Hello everyone, welcome to the course Nature and Properties of Materials. Welcome to the course Nature and Properties of Materials. In week 8, we'll talk about non-mechanical properties and laboratory demonstration. This course is offered by Professor Vishak Bhattacharya from Department of Mechanical Engineering, IIT Kanpur. I'm TA Alka Jangir from IIT Kanpur. So firstly, we'll go through some sample assignment questions which will help you in solving your weekly assignments and also will help you in your exams. Then we'll go through some lecture notes. So first question is, if you know the answer and if you face any difficulty, you can unmute and ask. And you can either type in chat as well. So first question is, which material is not diamagnetic? Your options are iron, gold, tin and mercury. So out of these, which material is diamagnetic? So out of these, iron is the one which is not diamagnetic but it is ferromagnetic. Other options are diamagnetic. Okay, so for explanation, what are diamagnetic materials? So these are the magnetic materials which align against the magnetic field, which are known as diamagnetic materials. The magnetic susceptibility is chi, which is lesser than 0, which means it is always a negative value for diamagnetic material. And these materials are repelled by the magnets and move from a stronger to weaker field. And these materials are independent of temperature. As in case of ferromagnetic, if you keep on heating your material about Curie temperature, you will see that it will lose its magnetism. So these materials are not dependent on temperature like ferromagnetic materials, and as these materials magnetize in the opposite direction, they do have a small amount of magnetization intensity. And gold, tin, mercury, water, etc. are examples of diamagnetic materials, and diamagnetic materials have a constant relative permeability. Next question is, piezoelectricity is shown by substances which are? Your options are polar, non-polar, symmetric or asymmetric. So correct answer here will be asymmetric. So as we saw earlier, this was the one of the example of piezoelectric material in quartz. So silicon and oxygen atoms are there, so there is a non-symmetric type of distribution of these positive and negative charges. So as you provide some tension or compression type of forces, then you will see there is distribution of charges will change. So based on that, you will be getting positive charge in this side, and in compression you will be getting negative charge in this side. So piezoelectric materials have an asymmetric distribution of charges, which gives them this type of piezoelectric effect. Next question is, which material shows less permeability? Your options are ferromagnetic, paramagnetic, diamagnetic or ferrimagnetic. So correct answer will be diamagnetic. Okay, so out of these various materials, you will be seeing that it has less permeability compared to even vacuum. So the magnetic permeability of a material is the ability to acquire magnetism when it is exposed to a magnetic field, and it is the maximum for ferromagnetic materials, and the magnetic permeability of diamagnetic materials is less than the permeability of vacuum, which is mu naught. The paramagnetic materials show better permeability than diamagnetic materials. Next question is, which one of the following materials is considered as a non-magnetic material? Your options are diamagnetic material, ferromagnetic material, ferrimagnetic material, or antiferromagnetic material. Okay, so correct answer will be diamagnetic materials. So a magnetic field repels diamagnetic materials because it includes a magnetic field that is directed in the opposing direction from that which it is applied, producing a repelling force. And diamagnetic substances are those substances which in their normal states have no magnetic moment at all. And the magnetic permeability of diamagnetic materials is less than the permeability of vacuum, mu naught. Bismuth, copper, gold, mercury, water, alcohol and hydrogen are some of the diamagnetic substances. Okay, so which one of the following material is considered as non-magnetic? So ferromagnetic, ferrimagnetic and antiferromagnetic, all these have magnetic field even in the absence of some magnetization. So diamagnetic material is the only one which is the considered as a non-magnetic material, and their behaviors we can see here as well. So in case of ferromagnetic and ferrimagnetic, even when there is no applied magnetic field, there are domains which are aligned in particular direction, and after application of field as well, these will align more strongly in the direction. In paramagnetic materials, they are randomly oriented before any application of magnetic field, and they will be aligning in the same direction to the magnetic field when there is field application. If there is diamagnetic material, there is no orientation or no magnetization at all, and then when you apply some magnetic field, then it will be showing some magnetization in the opposing direction. Next question is, a certain amount of current flows through a ring shaped coil with fixed number of turns. How does the magnetic induction B varies inside the coil if an iron core is threaded into coil without dimensional change of coil? So your options are it decreases, it increases, remains same, or first increases and then decreases depending on the depth of the iron insertion. So out of these, the correct answer will be increases. Okay, so whenever we add some core to your coil, it always increases the amount of magnetization. So an iron core inductor is a type of inductor which uses iron or ferromagnetic material as the core at the center of its coil. The use of an iron core in an inductor allows for a higher inductance value, as the iron core provides a greater magnetic field compared to the other materials like air or a ferrite core. Next question is, if the material has a refractive index 3 and the light is falling normal from a glass sheet of refractive index 1.8, then find the reflectivity of the material. Your options are 0.01, 0.03, 0.06 or 0.09. So which one should be the correct answer? So 0.06 will be the correct answer. So if the light is normal or perpendicular to the interface, then this formula is used, R equals to N2 minus N1 upon N2 plus N1 whole squared. So here you know the value of N2 is 3 and N1 is 1.8. So 3 minus 1.8 and 3 plus 1.8. So this one will be 1 upon 4 square. So it will be 1 upon 16. So it will be 0.0625. Next question is electrical resistivity of metal blank if temperature increases. So whether metal resistivity of metal increases or decreases or remains constant or increases depending on melting temperature if temperature increases. So correct answer here will be it increases. So these are the plots for resistivity and temperature. So as the temperature increases, resistivity also increases. Okay, so the electric conductivity of metal decreases with the increase in the temperature. It is due to an increase in the collision between free electrons, thereby increasing resistance. It is the reverse of semiconductors, for which conductivity increases with temperature. So in case of semiconductors, what happens? More electrons are excited in the conduction band if you provide higher temperature. While in case of metals, what happens? They already have free electrons. So the collision of these free electrons increases with increasing temperature, leading to decrease in the conductivity. Okay, so for aluminum, copper and iron, we can see copper has the least resistivity out of these metals. Aluminum has higher compared to this, and with increasing temperature this keeps on increasing. Which part of optical fiber passes the signal? So your options are cladding, coating, wire or core. So for this you should remember what is the design of optical fiber. So the correct answer here will be of course core. So these are the parts of a optical fiber. Internal core, where the light will get internally reflected and out, then cladding, and then outside layer will be coating. So in case of optical fiber, it includes core, which is signal passes through the core. So here also you can see the light is passing through it, and cladding is the higher reflectivity index material, so it constrains the light rays to travel within the core. Coating, so it protects core and cladding from damage. This coating will be protecting this fiber. Next question is, which material has the highest electrical conductivity among the options? Your options are aluminum, silver, copper and steel. So out of these, highest one will be in silver. Okay, so based on conductivity, solid materials can be classified as conductors having conductivity higher than 10 to the power 7, inverse of ohm meter. Semiconductors having between 10 to the power minus 6 to 10 to the power 4. Insulators lesser than 10 to the power minus 10. Okay, so silver has highest electrical conductivity 6.8 times 10 to the power 7 ohm meter inverse. Copper has lesser than that 6, and then less than that we have gold 4.3, and then less than that we have aluminum 3.8. Now aluminum and copper are the ones that have less, they are less expensive. So out of these, gold is the most expensive, then there is silver, then there is copper, then aluminum. So aluminum is the cheapest among these four which has the highest electrical conductivity. So in making wires, copper is used preferentially, and for reducing cost, aluminum can also be used. Iron 1.0, and after aluminum they have brass, then iron, then platinum, then plain carbon steel, and then stainless steel. So one thing also to remember is that pure metals will always have higher conductivity compared to their alloys, because due to alloying, what will happen, the scattering of the electrons will be there because of the lattice distortion. Next question is, piezoelectric effect is analogous to. Your options are electrostriction, magnetostriction, anisotropy, or magnetization. So the correct answer will be magnetostriction. So in case of piezoelectric materials, they convert electric energy to mechanical energy and vice versa. And they can be used as actuators because they provide a voltage to create motion. Sensors such as many accelerometers and energy harvesters, since the charge generated from motion can be harvested and stored. And a ferromagnetic sample changes its length with the application of magnetism, and the magnetostriction E in materials due to domain migration and reorientation under applied magnetic field H. Now first question is, which effect is responsible for white appearance of clouds? Your options are Rayleigh scattering, Tyndall effect, Compton scattering, or photoelectric effect. So the correct answer here will be Tyndall effect. Next question is, which of the following is false for laser? These are coherent light sources, which is correct, and these have low lifetime than LEDs. This is also correct. LEDs have higher lifetime. Ruby is used for making laser, so ruby is also, it is correct. And these does not affect health. So these can affect health because these can injure eyesight, and it can be also be through because of other there can be other effects on health as well of laser. So this one is the correct option. This statement is false. Next question is, which metal has highest thermal conductivity? Your options are silver, copper, gold, and aluminum. So silver is the one which has highest thermal conductivity as well electrical conductivity. Next question is, conductivity of metal blank with increasing temperature. Your options are increases, decreases, remains same, or increases or decreases based on atomic number of metals. So correct answer will be decreases. And which of the following is paramagnetic material? So your options are zinc, cobalt, titanium, and copper. So correct answer will be titanium. So out of these, this is the one which is paramagnetic. Okay, others are diamagnetic materials. Now we'll go through some lecture notes. So the chapter is on non-mechanical properties. So one of the non-mechanical properties, optical properties. So in case of optical, as we talk about visible light, so other than that, visible light and X-rays, gamma rays, these are the part of electromagnetic spectrum. So these are electromagnetic waves, and as we are moving upwards, you see that the wavelength is getting shorter and your frequency is increasing. So increasing photon energy as well. Energy is given as H h nu. So nu is your frequency. So as the frequency increases, your energy will also increase. So gamma rays, x-rays, ultraviolet radiation, then you have infrared radiation after visible light, and then microwaves, then radio waves. So, and these are the various wavelengths that are given. For radio waves it is in meters, and for microwaves it is in mm and centimeter. And for color, various colors, you can see these are the energies. So for violet it is 3.17 electron volt. For blue color it is, so as you can remember this as Vibgyor, VIBGYOR. So violet has 3.17, blue has 2.73, green has 2.52, yellow has 2.15, orange has 2.08, and red has 1.62 electron volt. So each electron, sorry, so each electromagnetic radiation is characterized by a combination of time varying electric field E and a time varying magnetic field propagating through space and having a specific range of wavelengths. So as you can see here, magnetic field and electric field are perpendicular to each other, and the direction of propagation is also perpendicular to these particular directions. So it is in 3 dimension. So all electromagnetic radiation traverses in vacuum at the same velocity, 3 multiplied by 10 to the power 8 meter per second. And epsilon naught is electric permittivity of vacuum, which is 8.854 times 10 to the power minus 12 farad per meter. And mu naught is the magnetic permittivity of vacuum, 1.257 times 10 to the power minus 6 Henry per meter. And the H is Planck's constant, 6.634 times 10 to the power minus 34 joule second. And nu is the frequency, hertz or per second. Lambda is wavelength in meter. C is velocity, meter per second. So capital C, which is the velocity of light, it can be given as equals to 1 upon under root epsilon naught and mu naught, which is vacuum's electric permittivity and magnetic permittivity. Next is energy, can be given as h nu, which is frequency, and times constant. H is your Planck's constant. Then frequency can be written as c upon lambda. Okay, because c is the velocity. So velocity of electromagnetic spectrum will be speed of light. Okay, so it is the speed divided by wavelength. Next is light interactions with solids. So incident light is reflected, absorbed, scattered and transmitted. So the light can be written in 3 terms. So IT, which is transmitted part of the incident light. So incident I naught, it will be converted into 3 parts. So firstly it will transmit, some part will be absorbed in this particular material, some part will be reflected. So IR is reflected, absorbed is IA, transmitted is IT. So these 3 combined energy will be equal to incident energy. So optical classification of materials. So materials can be either transparent, they can be translucent. So here as you can see, this is completely transparent, so light will pass through it to the highest amount. In translucent, some light will be transmitting. So you can see some of the characters that are written below this. In opaque, most light will be reflected. So these are the opaque materials. So in case of ceramic materials, if it is in single crystalline form, your material, then it will act as transparent. And if material is polycrystalline, then the intercrystalline regions or grain boundaries make it translucent. And in case of opaque, if it is there is porosity as well, then it will make your material opaque. Next is optical properties of metals. So all frequencies of visible light are absorbed. One second. Okay. So all frequencies of visible light are absorbed by metals because of the continuously available empty electron states which permit electron transitions, and the incident radiation having frequencies within the visible range excites electrons into unoccupied energy states above the Fermi energy. So the incident radiation is absorbed, hence metals are opaque. The Fermi energy is the maximum energy occupied by an electron at 0 Kelvin, and the change in the energy of the electron delta E is equal to the energy of the photon. And the re-emission of a photon of light takes place by the direct transition of an electron from a high to a low energy state. And metals are opaque to a low frequency radiation, so radio waves to about some middle of the ultraviolet rays, and metals are transparent to high frequency X-rays and gamma ray radiation. So here you can see these these gamma rays, X-rays, these can be have high frequency and high energy, so these can easily pass through the metals, while these are reflected. So here you can see some photon is absorbed in material, then it will give rise to the electrons in the filled states. It will jump into empty state in conduction band for above Fermi energy, and then this photon will be again re-emitted after this electron will fall in the Fermi energy level. Next is applications of optical phenomena. So first phenomena is luminescence, then second is photoconductivity, and then lasers. Okay, so in luminescence, it is the process where a material absorbs energy and then immediately emits visible radiation. It consists of electron excitation and then dropping down to lower energy states. If the emission of radiation occurs within 10 to the power minus 8 seconds after excitation, the luminescence is called fluorescence, and if it takes longer than 10 to the power minus 8 seconds, it is known as phosphorescence. And ordinarily pure materials do not display this phenomena, but some special materials called phosphors, they have this capacity, such as barium, magnesium, Al10O17, and yttria, Y2O3, and zinc sulfide and cadmium sulfide. Applications include fluorescent lamps, CRT, cathode ray tube, plasma video display screens, and white LEDs. Next phenomena is photoconductivity. It is the bombardment of semiconductors by photons with energy equal to greater than the band gap, may result in the creation of electron hole pairs that can be used to generate current, and this process is called photoconductivity. It is different from the photoelectric effect in the sense that an electron hole pair is generated whose energy is related to the band gap energy instead of the free electron alone whose energy is related to the Fermi level. The current produced in photoconductivity is directly related to the incident light intensity, and this phenomena is utilized in photographic light meters. Cadmium sulfide is commonly used for the detection of visible light as in light meters. Solar cells are also based on photoconductivity. Then lasers. Laser, it is a short for the light amplification by stimulated emission of radiation, and unlike luminescence which produces incoherent light, the light produced by laser emission is coherent and the constant phase difference and the same frequency is there, and this is based on the fact that in certain materials electrons are excited by a stimulus produce photons which in turn excite additional photons of identical wavelength. Example include ruby, which is single crystal of Al2O3 doped with little amount of Cr2O3. Yttrium, aluminum, garnet, its formula is Y3Al5O12, also written as YAG, doped with neodymium, Nd, helium neon, laser, some semiconductors like gallium arsenide and indium gallium arsenic phosphorus. So applications include welding, in metal cutting, heat treatment, surgery, and some eye surgery and all which require laser, and reading, compact discs, etc. Next application is optical fibers. So it is the medium for carrying information from one point to another in the form of light. The fiber optics is not electrical in nature, unlike the copper form of transmission. It has been calculated that it would require 30,000 kg of copper to transmit the same amount of information as only 0.1 kg of optical fiber material. And the information such as telephone conversation in electronic form is first digitized into bits, that is ones and zeros. This is accomplished in the encoder, and then electrical signal is converted into an optical or photonic one using the electrical to optical converter, which is normally a semiconductor laser. The laser emits monochromatic and coherent light, infrared region, low absorption losses, and the output converter is in the form of pulses of light, a binary 1 of high power pulse and a 0 for low power pulse. The pulse signals are then fed into and carried through the fiber optical cables, and at receiving end reverse process takes place. Optical fiber components. So internal is the core, which is up to 8 to 62.5 micrometer, and then there is cladding, its diameter is 125 micrometer. Then there is coating, which can be 250 to 900 micrometer. So this optical fiber, it includes core, which passes the signal through the core, cladding, which constrains the light rays to travel within the core. Then there is coating, which protects core and cladding from damage. Now, because of the differences in refractive indexes, this light is trapped inside this particular core, and it will travel through internal reflection, total internal reflection. This is the firstly the signal will be going through encoder, then it will be converted into electrical and optical converter, and then this light signal will be passed through fiber optic cable, and there will be repeaters in between these. Then there is optical to electrical signal converter, and then this electrical signal will be decoded, and then you will be getting output signal. The applications. So the optical fiber experiences geometrical size and shape and optical refractive index or mode conversion changes depending upon the nature and the magnitude of the perturbation. So the here you can see light in, then because of the parameter of interest, if it changes, it can sense that, and the modulated light out is detected. This is for intrinsic sensor. So the optical fiber serves as the transducer and converts measurements like temperature, stress, strain, rotation, and or electric and magnetic currents into a corresponding change in the optical radiation. Since light is characterized by intensity, phase, frequency, and polarization, any one or more of these parameters may undergo a change. So here you can see light in, and because of the external transducer, the parameter of interest, if it changes, this will detect change, and the light in and modulated light out here, because of extrinsic sensor, this will be detected. So in case of intrinsic sensor, use of fiber itself as the transducer, while in extrinsic sensor, use fiber to supply light to a sensing device and return signal light to a detection system. Next properties are, after optical we have thermal properties. So in case of thermal properties, these describe the response of material to the application of heat. So as a solid absorbs energy in the form of heat, its temperature rises and its dimension increases. And the important thermal properties are heat capacity, thermal expansion, and thermal conductivity. So here these are the materials and these are the heat capacities. So for polymers it is very high, 1925 for polypropylene, for polyethylene it is 1850, polystyrene 1170, and Teflon 1050. And for ceramics, magnesia it is 940, alumina it is 775, glass it is 840, and for metals such as aluminum it is 900, steel 486, tungsten 138, gold 128 joule per kg Kelvin. So these polymers, they have significantly larger heat capacity because of covalent bonds. In polymers, they do not let atoms exchange electrons as metallic bonds do. Heat capacity, it represents the amount of energy that is required to produce a unit temperature rise. It is indicative of a material's ability to absorb heat from the external surroundings. Mathematically, energy change, gain or loss, dq, divided by resulting temperature change, dt. So heat capacity, it increases with temperature. So as you can see, as the temperature is keep on increasing, the heat capacity is increasing. And for solids, it reaches maximum value of 3R. R is the gas constant. And from an atomic perspective, energy is stored as atomic vibrations, and as temperature increases, the average energy of atomic vibrations also increases. Next property is thermal expansion. So temperature of a solid is a measure of its potential energy. So most solid materials, they expand upon heating and contract on cooling. So the heating to successively higher temperature raises the vibrational energy. Thus the interatomic separation increases from R0 to R1 to R3 and so on. The greater the atomic bonding energy, the deeper and narrower this potential energy trough will be. So if you have atomic energy bond and atomic bonding energy higher, so if you are moving from, let's say, polymers to ceramics, ceramics will be having covalent bonds which are greater, the energy is greater, so this graph will be more narrower and more deeper. So in that case, the elastic modulus will be keep on increasing if it is going downwards, and the expansion will be lesser in case of ceramic. Thus the increase in interatomic separation with a given rise in temperature will be lower. And these are various materials and their thermal expansion ranges. For metals, it is 5 to 25 times 10 to the power minus 6. And for ceramics, it is 0.5 to 15. And for polymers, it is highest 50 to 400. So ceramics have least alpha values, thermal expansion. Next is thermal conductivity. So thermal conduction is the phenomena by which heat is transported from high to low temperature regions of a substance. The Fourier law states that for a steady state, the heat flux is directly proportional to a temperature gradient. So Q upon A is equals to minus K times dt upon dx. So here small k is the thermal conductivity, which is in watts per meter Kelvin. The negative sign indicates that heat flows in the direction of decreasing temperature. The thermal conduction in a solid takes place by both lattice vibration waves, which are phonons, and free electrons. Thus total conductivity is K equals to K because of conductivity because of lattice vibration and K because of free electrons. In case of metals are extremely good conductors of heat because relatively large number of free electrons exist that participate in thermal conduction, and the purest form of metal will have high conductivity compared to alloy form, and in the alloy different atoms will have different electron affinity, thus movement of the excited electrons become difficult. Since free electrons are responsible for both thermal and electrical conduction in pure metals, the two conductivities are related by Widman-Friend's law, which is given as capital L equals to K upon sigma T. So here L is the Lorentz constant, which is 2.45 times 10 to the power minus 8 ohm watt per Kelvin square. And small k is the thermal conductivity in watt per meter Kelvin. Sigma is the electrical conductivity in ampere per voltmeter, and capital T is the absolute temperature in Kelvin. So these are various materials and their thermal conductivities. Silver has the highest 410, then there is copper 385, and then there is gold 314, then aluminum 210, and then iron 80 and steel 52. Next are ceramics. So they are thermal insulators as they lack large number of free electrons. Thus the phonons are primarily responsible for thermal conduction. So in this case conductivity because of electrons is lesser compared to conductivity because of phonons. Also the phonons are not as effective as free electrons in the transport of heat energy due to phonon scattering by lattice imperfections. And the room temperature thermal conductivities range between approximately 2 to 50 watt per meter Kelvin. The amorphous ceramics have lower conductivities than crystalline ceramics as the atomic structure is highly disordered and irregular. The higher porosity also reduces conductivity due to the presence of still air, which has conductivity as 0.02 watt per meter Kelvin, which this air is found in pores in case of ceramics. Next is polymers. So thermal conductivities for most polymers are of the order of 0.3 watt per meter Kelvin. The energy transfer is accomplished by the vibration and rotation of the chain molecules. The magnitude of the thermal conductivity depends on the degree of crystallinity. The highly crystalline and ordered structure means effectively coordinated vibration and higher thermal conductivity. So in case of materials, you can see the thermal conductivity is least in case of polymers, then it is higher in case of ceramics, then it is highest in case of metals. So in case of metals, we can see for aluminum it is 247, for steel 52, tungsten 178, gold 350. And in case of metals, the energy transfer mechanism is atomic vibrations and motion of free electrons. In case of ceramics, it is because of atomic vibrations only. So in magnesia it is 38, in alumina it is 39, in soda lime glass it is 1.7, and in silica it is 1.4. In case of polymers, for polypropylene it is 0.12, for polyethylene it is 0.46 to 0.5, for polystyrene it is 0.13, for Teflon it is 0.25. So in case of polymers, it is because of atomic vibrations and rotation of chain molecules. Next property is thermal stresses and shock. So thermal stresses are stresses which are induced in a body when due to changes in the temperature the deformation is hindered. The thermal stresses in a constrained body will be of compressive nature if it is heated, and it will be of tensile nature if it is cooled. So in thermal shock, if the dimensional change in a material are not uniform, then it may lead to the fracture of brittle materials like ceramics, and it is known as thermal shock. The capacity of a material to withstand thermal shock is defined as thermal shock resistance, or TSR. It is approximated as sigma F K divided by capital E alpha. So here sigma is your fracture strength, sigma F, and K is your thermal conductivity, E is elastic modulus, alpha is the thermal expansion coefficient. So for high thermal shock resistance, you can either have a material with a low value of thermal expansion coefficient alpha and low value of elastic modulus. So in case of ceramics, elastic modulus is very high. That's why they fracture because of the thermal shock. And for high thermal shock resistance, you can also have material with high value of thermal conductivity K and high value of fracture strength. Next property is electrical properties. So according to Ohm's law, voltage is proportional to current flowing in the resistor. So the proportionality constant is the resistance R. R is the resistance of material in ohms. V is the voltage drop in volts. I is the current in amperes. The material's electrical resistance is an extrinsic property which depends on the objective geometry. So it depends on the material's geometry such as cross section and length. The resistivity is the independent of specimen geometry intrinsic property, but it is related to R through the expression as resistance equals to resistivity times length upon area. Here L is the distance between voltage measuring points, so as shown here, length, and A is the cross sectional area. So if you're, for example, if you're taking any wire, so wire's cross section will be the pi r square. See, so A is the cross sectional area perpendicular to the direction of the current. Unit of resistivity will be ohm meter. So here also you can see this is the resistance, and this is connected through the wires and with the help of battery and the ammeter, which is measuring how much current is flowing through this, and voltmeter is measuring the voltage drop across the resistor. So electrical conductivity, it is just the inverse of the electrical resistivity. So it is indicative of the ease with which a material is capable of conducting electric current, and the electrical conductivity can be given as 1 upon resistivity. So unit will be inverse of the ohm meter. And on the basis of conductivity, solid materials can be classified as conductors, semiconductors, and insulators. So in case of conductors, you have conductivity higher than 10 to the power 7, inverse of ohm meter, and for semiconductor it is in between 10 to the power minus 6 to 10 to the power 4, and for insulators it is less than 10 to the power minus 10. So conduction can be of two types, electronic and ionic. In case of electronic conduction, the current will be arising from the flow of electrons, and in ionic conduction the current will be arising from the net motion of charged ions. These are various materials. So in case of metals, ceramics and polymers, these are the electrical conductivities. So electrical conductivity is in the range of 10 to the power 7 for the metals, and for polymers it is 10 to the power minus 10 to minus 13 to even minus 17, and for ceramics it is 10 to the power minus 13 to 10 to the power minus 9. And in case of metals, highest electrical conductivity is for silver, then 6.8, then it's for copper 6, then it is for gold, then for aluminum, then brass, iron, platinum, plain carbon, and stainless steel. In case of graphite, it has high electrical conductivity because it has free electrons. And other ceramics, in these electrical conductivity is not there because free electrons are not there. So these are basically act as insulators. So both of these, they are used as insulators. Now effect of temperature on metal conductivity. So increasing temperature causes greater electron scattering due to increased thermal vibrations of atoms, and the resistivity of metals increases or conductivity decreases linearly with temperature. So in case of metals, what happens? The electrical conductivity arises because of free electrons. So what happens if you are increasing the temperature? These electrons will collide with each other and there will be scattering because of that. So the directionality will be lost on application of voltage. So because of that, the resistance will increase. So here also you can see, with increasing temperature, your electrical resistivity is increasing. So the total resistivity of a metal is the sum of the contribution from thermal vibration rho T. So here you can see, if your material is pure and there is no deformation and impurity, the increases at any temperature increases only because of the scattering. Okay, so this is the rho T because of thermal vibration. Then impurities because of I. So for example, if you added 1.13 atom percent nickel in copper, so this amount of increase comes because of impurity. Okay, which is almost twice because of the scattering. Next is because of plastic deformation, rho D. So if this material is deformed further, so because of deformation, this amount of resistivity will arise. So the total resistivity of metal is the sum of contributions from thermal vibrations, impurities and plastic deformation. So the scattering mechanisms act independently of one another. So here from this particular graph you can see, at minus 100 degrees Celsius, if your material is pure copper, the amount of electrical resistivity, this comes purely because of the thermal vibrations, and if you add some impurity such as nickel in it, then this amount of resistivity comes because of the impurity, and if you deform this material further, then this amount of resistivity comes because of the deformation. So the resistivity is the addition of because of these three elements. In case of insulators, they have wide band gap which is between a conduction band. So this is greater than 2 electron volt, and for very few electrons that are excited across the band gap. And in case of semiconductors, they have narrow band gap lesser than 2 electron volt. So there are more electrons that are excited across band gap. In case of semiconductors, this type of relation won't be there. For semiconductors with increasing temperature, the resistivity decreases. Next is magnetic properties. So the magnetic field is a force which is generated due to the energy change in a volume of space, and a magnetic field is produced by an electric charge in motion, for example current, which is flowing in the conductor. So because of that, around that particular wire there will be generation of magnetic field. Also in orbital movement and spin of electrons, this will also give rise to some magnetic field generation. Next is origin of magnetic moments. So orbital motion around the nucleus. So here you can see, this is the nucleus and this is the electron, atomic nucleus and electron that is there. So because of this movement, there is magnetic moment in this perpendicular direction to this orbit, and the electron considered to be a small current. So orbital motion around the nucleus, electron considered to be a small current loop generating a very small magnetic field having a magnetic moment along its axis of rotation. Next is the spinning of electron as well. So similar to earth, as it spins on its axis as well and rotates around sun as well. So electron does the same. Electron spins, so the direction of spin is there, and because of that there will be magnetic moment as well. So the spin of electrons also produces a magnetic moment along the spin axis, and these spin magnetic moments may be only parallel or anti-parallel. Now the type of properties or type of materials. So first is diamagnetic type of materials. In this case, this is the weak form of magnetism which arises only when an external field is applied. So if there is no external field, then you can see there is no magnetization. So it arises due to a change in orbital motion of electrons on the application of magnetic field, and there are no magnetic dipoles in the absence of the magnetic field, and when a magnetic field is applied, the dipole moments are aligned opposite to the field direction, and the magnetic susceptibility chi m is given as magnetization divided by field intensity, and this is negative, which means that B, magnetic flux density in a diamagnetic material, is less than that of vacuum, and it is repelled by the applied magnetic field. So the diamagnetic materials are alumina, Al2O3, copper, gold, silicon and zinc. Next is paramagnetism. So in this so here as well, if you are applying magnetic field in this direction, then the magnetization occurs in opposing direction compared to the field. Next is paramagnetism. So in this, the cancellation of magnetic moments between electron pairs is incomplete, and hence magnetic moments exist without any external magnetic field. Here you can see, if you are not applying any magnetic field, the domains are still present, but they will be cancelling each other out in absence of any magnetic field. When there is magnetic field applied, these will be rotating and they will be providing a strong magnetization. However, the magnetic moments are randomly aligned, and hence no net magnetization without any external field. When a magnetic field is applied, all the dipole moments are aligned in the direction of the field, and the magnetic susceptibility is small but positive. So B in a paramagnetic material is slightly greater than that of the vacuum. The paramagnetic materials are aluminum, chromium, molybdenum, titanium and zirconium. Next is ferromagnetism. So certain materials possess permanent magnetic moments in the absence of an external magnetic field, and this is known as ferromagnetism. The permanent magnetic moments arise due to the uncancelled electron spins by virtue of their electron structure. The coupling interactions of electron spins of adjacent atoms cause alignment of moments with one another, and the origin of this coupling So for those who joined late, we are going through lecture notes. After completing these 4-5 slides, we will go through the sample assignment questions once again. So the coupling interaction of electron spins of adjacent atoms, they cause alignment of moments with one another. The origin of this coupling is attributed to the electron structure. Example, in case of iron, the 26 electrons, and after that argon, these are as this one. So argon filling electron structure, then other electrons goes into 4s and 3d. So 3d, they have 6 electrons, so 4 are uncoupled. So in case of, they have incompletely filled d orbitals, hence unpaired electron spins. So even in the absence of any external field, you can see these domains are aligned in particular direction and they provide permanent magnetism. Next is antiferromagnetism. So if the coupling of electron spins results in anti-parallel alignment, then spins will cancel each other and no net magnetic moment will arise, and this is known as antiferromagnetism. Manganese oxide is one of the example, and in case of manganese oxide, O2 minus ions, they have no net magnetic moments, and the spin moments of Mn2 plus ions are aligned anti-parallel to each other in adjacent atoms. So here you can see Mn2 plus atoms, they have particular domain structure to it, but oxygen, they have all shells fulfilled. So these will be having some magnetization related to these. Next is ferrimagnetism. So certain ionic solids having a general formula MFe2O4, where M is any metal, it shows permanent magnetism, termed ferrimagnetism due to partial cancellation of spin moments. In Fe3O4, Fe ions can exist in both 2 plus and 3 plus states as Fe2 plus O2 minus and Fe3 plus 2 O2 minus 3 in 1:2 ratio. The anti-parallel coupling between Fe3 plus, half in A sites and half in B moments, cancel each other. Here Fe2 plus moments are aligned in the same direction and result in a net magnetic moment. So here you can see in octahedral lattice sites you will be having both Fe3 plus and Fe2 plus, but in tetrahedral sites you won't be having Fe2 plus. So there will be complete cancellation for Fe3 plus, but for Fe2 plus there will be net magnetic moment in upward direction. Next is temperature influence on magnetic behavior. So the atomic vibration increases with increasing temperature, and it leads to the misalignment of magnetic moments as they are free to rotate. Above a certain temperature, all the moments are misaligned and the magnetism is lost. The temperature is known as Curie temperature, Tc, and the magnitude of Curie temperature varies from material to material. For example, for iron it is 768 degrees Celsius, for cobalt it is 1120 degrees Celsius, for nickel it is 335 degrees Celsius, and for ferric oxide it is 585 degrees Celsius. So below Tc you can see these domains will be present there having particular orientation to it, but above Tc this domain structure is lost. So ferromagnetic materials, they exhibit small volume regions in which magnetic moments are aligned in the same direction, and these regions are called domains. The adjacent domains are separated by domain boundaries. So as seen here, these are the domain walls or domain boundaries, and these are the areas which are domains, and the adjacent domains are separated by domain boundaries, and the direction of magnetization changes across the boundaries. The magnitude of magnetization in the material is the vector sum of the magnetization of all the domains. So as you keep on increasing the temperature up to Curie temperature, you see that the saturation magnetization will keep on decreasing and it will reach to 0 at Curie temperature. Next is the soft and hard magnets. So the energy product in kilojoule per meter cube, it is the area of the largest BH rectangle that can be constructed within the second quadrant of the hysteresis loop. So it represents energy that is required to demagnetize a permanent magnet. The largest BH max, the higher the size of BH max area, the harder it is for the material in terms of its magnetic characteristics. So there are two types of magnets, soft magnets and hard magnets. Soft magnets will be having narrow hysteresis curve, which are shown here. So the narrow will be soft one and hard will be the higher area. So the narrow hysteresis curve for soft magnets, broad for hard magnets. In case of soft magnets, there will be high initial permeability and low coercivity. So easy movement of domain walls. For hard magnets, low initial permeability, high hysteresis energy losses and high coercivity. For soft magnets, it is easy to magnetize and demagnetize. For hard magnets, it is difficult to demagnetize. Soft magnets, their examples include iron silicon alloys, nickel iron alloys, and iron, which is used widely in generators, transformers, and switching circuits. For hard magnets, alnico, which is aluminum, nickel, and cobalt alloy, ferrites, rare earth cobalt, cobalt platinum, etc. Hard magnets are used in all permanent magnets in applications such as power drills, motors, and speakers. Now this is the hysteresis curve. So here you first start to magnetize your material, then you reach saturation when all the domains will be aligned in one direction. Then after this you keep on reducing the applied magnetic field. Then after you remove the entire field, yet there is some measure of the remaining magnetization when the driving field is dropped to 0. This is the remanence. And after this, to bring this magnetization to 0, you have to apply magnetic field in negative direction. So this is the coercivity, which is a measure of the reverse field needed to drive the magnetization to 0 after being saturated. Then you follow this similar type of loop in negative direction as well, and this is the this particular loop. It shows whether your material is soft magnet or hard magnet as shown from here. Okay, now that's it from lecture notes. I'll be repeating the questions once again. Okay, so first question is which material is not diamagnetic? Your options are iron, gold, tin, mercury. So out of these, all are diamagnetic except iron. Iron is ferromagnetic material. So what is the definition for diamagnetic material? These are the magnetic materials which align against the magnetic field, which are also known as diamagnetic materials. The magnetic susceptibility for these materials is lesser than 0, which is means that it is always a negative value for diamagnetic materials, and these materials are repelled by the magnets and move from a stronger to weaker field. These materials are independent of temperature, and as these materials magnetize in the opposite direction, they do have a small amount of magnetization intensity. Gold, tin, mercury, water, etc. are examples of diamagnetic materials, and the diamagnetic materials have a constant relative permeability. Next question is piezoelectricity is shown by substances which are your option. Yeah. Do you have any question? If you have any question, you can ask. Okay, next question is piezoelectricity is shown by substances which are. Your options are polar, non-polar, symmetric and asymmetric. So correct answer will be asymmetric. So in case of piezoelectricity, your materials, the distribution of the charges will be asymmetric. So because of this asymmetry, if you apply tension or compression, it will be showing this type of distribution, which will lead to this voltage generation. So piezoelectric materials have asymmetric distribution of charge, which gives them piezoelectric effect. This is the structure of quartz, silica, SiO2. Next question is which material shows less permeability? Your options are ferromagnetic, paramagnetic, diamagnetic and ferrimagnetic. So correct answer will be diamagnetic. The magnetic permeability of a material is its ability to acquire magnetism when it is exposed to a magnetic field, and it is the maximum for ferromagnetic materials, and the magnetic permeability of diamagnetic material is less than permeability of vacuum, which is mu naught. The paramagnetic materials show better permeability compared to diamagnetic materials. Which one of the following materials is considered as non-magnetic material? Your options are diamagnetic materials, ferromagnetic materials, ferrimagnetic materials and anti-ferrimagnetic material. So the correct answer will be diamagnetic materials. So this is how your material will show magnetic behavior. So if you are not applying any magnetic field, in case of diamagnetic there is no domain structure as at all, and after you apply this magnetic field, then your domains will be aligned in the opposing direction. In case of ferromagnetic and ferrimagnetic materials, these are already aligned in particular direction, and if you apply magnetic field, it will be more strongly aligned, while in case of paramagnetic they are randomly aligned before application of field. A magnetic field repels diamagnetic materials because it induces a magnetic field that is directed in the opposing direction from that which it is applied, producing a repelling force. The diamagnetic substances are those substances which in their normal states have no magnetic moment at all. The magnetic question repeat. Questions won't repeat in exam, like It depends on, questions can be similar to these, they want to be exactly same to these questions. So diamagnetic substances are those substances which in their normal states have no magnetic moment at all. The magnetic permeability of diamagnetic materials is less than the permeability of vacuum, mu naught. Bismuth, copper, gold, mercury, water, alcohol and hydrogen are diamagnetic substances. So for preparing for exam, you just first you need to solve your assignments and go through all the lecture notes, and questions will be similar to your assignment questions but not exactly same. They can be similar to those or they can be different as well, like some of the numericals, they can be different as well. Fifth question is, a certain amount of current flows through a ring shaped coil with fixed number of turns. How does the magnetic induction B varies inside the coil if an iron core is threaded into coil without dimensional change of coil? Your options are decreases, increases, remains same, or first increases and then decreases depending on the depth of iron insertion. So out of these, correct answer will be first one. Okay, so the iron core inductor is a type of inductor which uses iron or ferromagnetic material as the core at the center of its coil. The use of an iron core as an inductor allows for a higher inductance value, as the iron core provides a greater magnetic field compared to other materials like air or the ferrite core. Next question is, if the material has a refractive index 3 and the light is falling normal from a glass sheet of refractive index 1.8, then find the reflectivity of material. Your options are 0.01, 0.03, 0.06 and 0.09. So the correct option will be third one, and this is the formula that you need to remember. So if the light is normal or perpendicular to the interface, then your reflectivity of material can be given as n2 minus n1 upon n2 plus n1 times whole square. So reflectivity can be given as 3 minus 1.8 divided by 3 plus 1.8 and whole square. So correct answer here will be 0.0625. Next question is, electrical resistivity of metal blank if temperature increases. So as you know, as you increasing the temperature, in case of metals, what happens, the electrons are the responsible for the electrical conductivity, so they will be scattering, their motion will be scattering, so that's why the resistivity will increase. Okay, you can remember this particular graph. As you keep on increasing the temperature, resistivity will increase for metals, while for semiconductors it will be opposite. So for semiconductors it will decrease. The electric conductivity of metals decreases with increasing in the temperature. It is due to an increase in the collision between free electrons, thereby increasing resistance. It is the reverse for semiconductors, for which conductivity increases with temperature. Next question is, which part of optical fiber passes the signal? Your options are cladding, coating, wire and core. So core is the part of optical fiber which passes the signal. So here you can see inside part is the core, then there is cladding, then there is coating. So the optical fiber includes core, which signal passes through the core, cladding, which constrains the light rays to travel within the core, coating, which protects core and cladding from the damage. Next question is, which material has the highest electrical conductivity among the options? Your options are aluminum, silver, copper and steel. So both electrical and thermal conductivity highest for the silver. So you should remember at least this particular fact if you are asked. So this is the table for electrical conductivity. For silver it is highest 6.8, and for next is the copper, then third highest is gold, then aluminum. Okay, and we prefer to make wires from either copper and aluminum because they are cheaper compared to silver and gold. Based on conductivity, solid materials can be classified as conductors having conductivity more than 10 to the power 7 ohm meter inverse, and for semiconductors it's in between 10 to the power minus 6 to 10 to the power 4, and for insulators it is lesser than 10 to the power minus 10. Next question is, piezoelectric effect is analogous to. Your options are electrostriction, magnetostriction, anisotropy and magnetization. So correct answer will be magnetostriction. So in case of piezoelectric materials, it converts electric energy to mechanical energy and vice versa. While in case of magnetostriction, what happens if you are applying a magnetic field, the domains will align in one direction leading to the length change. So it will also lead to change in strain energy. So that's why it is similar to piezoelectric behavior. So these piezoelectric materials, they can be used as actuators to provide a voltage to create motion. Sensors such as many accelerometers and energy harvesters, since the charge is generated from the motion, can be harvested and stored. In case of paramagnetic sample, it changes its length with the application of magnetism, and the magnetostriction in materials is due to domain migration and reorientation under applied magnetic field H. Next question is, which effect is responsible for white appearance of clouds? Your options are Rayleigh scattering, Tyndall effect, Compton scattering or photoelectric effect. Out of this, Tyndall effect is the reason for appearance of clouds as white. Other question is, which of the following is false for lasers? So these are coherent light source, which is correct. These have low lifetime than LEDs, which is also correct. Ruby is used for making lasers. So some of the lasers examples you should remember, such as YAG, Ruby and helium neon. These sources you should remember, and also these does not affect health. So this is the false statement because these can affect your health of eye and other some effects. Third question is, which metal has highest thermal conductivity? Your options are silver, copper, gold and aluminum. So as I told earlier, thermal and electrical both conductivity is highest for silver. Conductivity of metal blank with increasing temperature. So it decreases with increasing temperature, and in case of semiconductors, your conductivity will increase. Okay, and which of the following is paramagnetic material? So your options are zinc, cobalt, titanium and copper. So out of these, other are diamagnetic and titanium is the one that is paramagnetic material. So these examples also you should remember if you are asked in exam. Examples of paramagnetic, diamagnetic and paramagnetic materials. Next is again lecture notes. So this is the electromagnetic spectrum. As you keep on going up, you will be seeing the increase in frequency and wavelength will be shorter. So as you keep on increasing, you see the energy is increasing, and these rays, gamma rays, X rays, these For these, your metals, they act as transparent. So these can go through metals, while these will be reflected, these microwaves and radio waves. And the energy is also increasing upwards, as the energy of electromagnetic waves is given as h nu. Nu is the frequency, and these are the energies of various colors. In case of electromagnetic radiation, it is characterized by a combination of time varying electric field and a time varying magnetic field, propagating through space, having a specific range of wavelengths. So these both, magnetic field and electric field, are perpendicular to each other, and the propagation direction is also perpendicular to both of these fields. This is the lambda wavelength. And the all electromagnetic radiation, it traverses in vacuum at the same velocity, which is velocity of light. Okay, and these are the formulas for the velocity of light in terms of electric permittivity of vacuum and magnetic permittivity of vacuum. And energy of electromagnetic radiation, h nu. This nu can be written as c upon lambda. C is the speed, lambda is the wavelength. Light interactions with solid. So incident light is I naught. It can be divided into three parts. It partially gets absorbed, partially transmitted, partially reflected. So addition of all these three should be equal to incident, this incident light. So in case of optical classification of material, this material can be either transparent, passing marks. I think it should be given on NPTEL website how much passing marks you require. I'll check once. So need at least 40 out of 100 in both the assignment portions. I think in final exam you need minimum of 30 out of 75 marks of final proctored exam. 40 out of 100 you require, the combined assignment and final exam. So these are three types of optical classification of materials. They can be transparent, made of single crystals, translucent, polycrystalline dense materials, opaque, polycrystalline porous materials. Then optical properties. So all frequencies of visible light are absorbed by metals because of the continuously available empty electron states which permit electron transitions. The incident radiation having frequencies within the visible range excites electrons into unoccupied energy states above the Fermi energy. So the incident radiation is absorbed. Hence metals are opaque. Important questions. So firstly, I think most questions, if you solved all the assignments correctly, and you should, if you have gone through your lecture notes, the videos of sir correctly, all the videos, then I think you'll have idea of what questions can be asked. If you went through assignments, and I think these are the most important is to go through the lecture videos. You should prepare notes as well from lecture videos, whichever like formulas that you can remember. Some of the examples, such as if in today's class, the examples of diamagnetic materials or the formula for uh, Lorentz constant or these type of formulas, those one will be the ones that can be the possible questions. So for example, the definition of heat capacity, or which materials have higher heat capacity, and these type of questions or these type of formulas, these one you should remember. So these one you should prepare notes as well, so that you will remember those in exams. So I think, and also like which material is higher conductivity, so these type of at least top 5 you should remember or something like that. These can be like, if you'll go through the lecture notes, you'll get an idea what will be the important ones. In going through assignments as well, you'll have some idea like what type of questions will be there. So I think I'll go through these slides, and once I can tell. So if you're like getting the concepts correctly, like why this, for pure if you're increasing temperature, the conductivity is reducing. So if you remember these type of concepts as well, these might also help in exam. In these diamagnetic, paramagnetic, firstly definitions and why it is happening, this type of ferromagnetism, how does it generate, and what are some of the examples. Try to remember some of the examples, and then this behavior with temperature, how it is changing, hard magnets, soft magnets. These are the some of the questions. These can be important in this particular chapter, and other chapters you can see, such as the packing fraction of FCC, how to calculate those, and some of the numericals related to those can be important. Ohm's law. So you should remember, at least remember these particular concepts and these particular formulas. These you should remember. Okay, so optical properties for metals. So all frequencies of visible light are absorbed by metals because of continuous availability of empty electron states which permit electron transitions. The incident radiation having frequencies within the visible range excites electrons into unoccupied energy states above the Fermi energy. So the incident radiation is absorbed, hence metals are opaque. The Fermi energy is the maximum energy occupied by an electron at 0 Kelvin, and the change in energy of the electron delta E is equal to the energy of the photon, and the re-emission of a photon of light takes place by the direct transition of an electron from a high to a low energy state. Metals are opaque to low frequency radiation, radio waves to about some middle of ultraviolet rays, and the metals are transparent to high frequency such as X-rays to gamma ray radiation. Then these are the applications of these optical properties. Luminescence, so it is the process where a material absorbs in case of, so some of the applications of optical phenomena include luminescence. It is the process where a material absorbs energy and then immediately emits visible radiation. It consists of electron excitation and then dropping down to lower energy states. If the emission of radiation occurs within 10 to the power minus 8 seconds after excitation, the luminescence is called fluorescence, and if it takes longer than 10 to the power minus 8 seconds, it is known as phosphorescence. Ordinarily, pure materials do not display this phenomena, but some special materials called phosphors, they have this capacity, such as barium, magnesium, aluminum 10, oxygen 17, yttria, zinc sulfide and cadmium sulfide. Their applications include fluorescent lamps, CRT, plasma video display screens and white LEDs. Next is photoconductivity. So in this case, bombardment of semiconductors by photons with energy equal to greater than the band gap may result in the creation of electron hole pairs that can be used to generate current, and this process is called photoconductivity. And it is different from the photon electric effect in the sense that an electron hole pair is generated whose energy is related to the band gap energy instead of the free electron alone whose energy is related to the Fermi level. The current produced in photoconductivity is directly related to the incident light intensity, and this phenomena is utilized in photographic light meters. Cadmium sulfide is commonly used for the detection of visible light as in the light meters. Solar cells are also based on photoconductivity. Next application is lasers, which is light amplification by stimulated emission of radiation. Unlike luminescence, which produces incoherent light, the light produced by laser emission is coherent, constant phase difference and the same frequency. And this is based on the fact that in certain materials, electrons excited by a stimulus produce photons, which in turn excite additional photons of incident wavelength. Some of the examples include ruby, which is single crystal of alumina doped with little amount of chromia, yttrium, aluminum garnet doped with neodymium, helium neon laser, some semiconductors like gallium arsenide and indium gallium arsenic phosphide. Applications include in welding, metal cutting, heat treatment, surgery, reading, compact discs, etc. Other application is in making optical fibers. So medium for carrying information from one point to another in the form of light. Fiber optics is not electrical in nature, unlike for copper form of transmission. It has been calculated that it would require 30,000 kg of copper to transmit the same amount of information as only 0.1 kg of optical fiber material. The information, telephone conversations such as in electronic form, is first digitized into bits, that is ones and zeros, and this is accomplished in the encoder. Then electrical signal is converted into an optical one using the electrical to optical converter, which is normally a semiconductor laser. The laser emits monochromatic and coherent light, infrared region, and low absorption losses. The output converter is in the form of pulses of light, a binary 1 high power pulse and a 0 low power pulse. The pulse signals are then fed into and carried through the fiber optical cable at receiving end. Reverse process takes place. So this is the process that takes place in optical fiber components. So components include core, which is 8 to 62 micrometer in diameter. Then there is cladding, which is 125 micrometer. Then coating, which is 250 micrometer to 900 micrometer. So these are the various roles of these components. For core, it will be passing the signal. Cladding, it will be constraining the light rays to travel within the core. Coating will be protecting the core and cladding from damage. These are the applications. So optical fiber experiences geometrical and optical changes depending upon the nature and the magnitude of the perturbation, and the optical fiber serves as a transducer and converts measurements like temperature, stress, strain, rotation, and electric and magnetic currents into corresponding change in the optical radiation. And since light is characterized by intensity, phase, frequency, and polarization, any one or the more of these parameters may undergo a change. Intrinsic sensors, which uses fiber itself as a transducer. Extrinsic sensors, which use fiber to supply light to a sensing device and return signal light to a detection system. Next is thermal properties. So thermal properties describe the response of a material to the application of heat. As a solid absorbs energy in the form of heat, its temperature rises and its dimensions increases. And important thermal properties are heat capacity, thermal expansion, thermal conductivity. And polymers have significantly larger heat capacity because covalent bonds in polymers do not let atoms exchange electrons as metallic bonds do. So polymers have very high heat capacities compared to ceramics and metals. So heat capacity represents the amount of energy that is required to produce a unit temperature rise, and it is indicative of a material's ability to absorb heat from the external surroundings. Mathematically, energy change, gain or loss dQ divided by dt, which is resulting temperature change. So heat capacity increases with temperature, and for solid it reaches a limiting value of 3R. And from an atomic perspective, energy is stored as atomic vibrations, and as temperature increases, the average energy of atomic vibration also increases. Next is thermal expansion. So a temperature of a solid is a measure of its potential energy. Most solid materials expand upon heating and contract on cooling. Heating to successively higher temperatures raises the vibrational energy. Thus the interatomic separation increases from R0 to R1 to R2 and so on, as shown in this figure. The greater the atomic bonding energy, the deeper and narrower this potential energy trough will be. Thus the increase in interatomic separation with a given rise in the temperature will be lower. These are the alpha 1 values. For metals it is 5 to 25, for ceramics it is 0.5 to 15, for polymers it is highest 50 to 400. Thermal conductivity, thermal conduction is the phenomena by which heat is transported from high to low temperature regions of a substance. The Fourier law states that for a steady state, the heat flux is directly proportional to a temperature gradient. Q upon A is given as minus K times dt upon dx. K is thermal conductivity in watts per meter Kelvin. Negative sign here, it indicates that the heat flow is in the direction of decreasing temperature, and the thermal conduction in a solid takes place by both lattice vibration waves, phonons and free electrons. Thus total conductivity can be given as addition of conductivity because of lattice vibrations and because of electrons. In metals, they are extremely good conductors of heat because of relatively large number of free electrons which exist that participate in the thermal conduction. The purest form of metal will have high heat conductivity compared to alloy form, and in the alloy different atoms will have different electron affinity. Thus movement of excited electron becomes hard. Since free electrons are responsible for both thermal and electrical conduction in pure metals, the two conductivities are related by Widman-Frenz law, which is L equals to K upon sigma T. And these are the thermal conductivities, having silver highest, second highest copper. Then ceramics, they are thermal insulators as they lack large number of free electrons. Thus the phonons are primarily responsible for thermal conduction. Also the phonons are not as effective as free electrons in the transport of heat energy due to phonon scattering by lattice imperfections. The room temperature thermal conductivities range between approximately 2 to 50 watts per meter Kelvin. Amorphous ceramics have lower conductivities compared to crystalline ceramics as the atomic structure is highly disordered and irregular. Higher porosity also reduces conductivity due to the presence of still air. Polymers, thermal conductivity for most polymers are of the order of 0.3 watt per meter Kelvin. The energy transfer is accomplished by the vibration and rotation of the chain molecules. The magnitude of the thermal and conductivity depends on the degree of crystallinity. High crystalline and ordered structure means effective coordination, vibration and higher thermal conductivity. Next is thermal stresses and shock. So thermal stresses are the stresses induced in a body when due to changes in the temperature the deformation is hindered. The thermal stresses in a constrained body will be of compressive nature if it is heated, and vice versa. Thermal shock if the dimensional change in a material are not uniform, that may lead to the fracture of brittle materials like ceramics, and it is known as thermal shock. The capacity of material to withstand thermal shock is defined as thermal shock resistance, which is given as sigma F fracture strength, K is the thermal conductivity, E is the elastic modulus, alpha is the thermal expansion coefficient. So for high thermal shock resistance, a low value of thermal expansion coefficient and elastic modulus is desired, and a high value of thermal conductivity and fracture strength is desired. Electrical property. For Ohm's law, voltage is equals to IR, where V is voltage drop, I is current, R is resistance of material, and material's electric resistance is an extrinsic property which depends on object geometry. Resistivity is independent of specimen geometry, which is intrinsic property but related to R through the expression R equals to rho L upon A, where I is distance between voltage measuring points, A is cross sectional area perpendicular to the direction of the current, unit of rho is the ohm meter. Electrical conductivity is indicative of the ease with which material is capable of conducting a electric current. So conductivity can be given 1 upon resistivity, and on the basis of conductivity, solid materials can be classified as conductors, semiconductors and insulators. So if conductivity is higher than 10 to the power 7, then it is conductor. It is semiconductor if it is in between 10 to the power minus 6 to 10 to the power 4 inverse of ohm meter, and if it is lesser than 10 to the power minus 10, then it is insulator. And there are two types of conduction, electronic and ionic. Current arising from the flow of electrons and current arising from net motion of charged ions. Effect of temperature on metal conductivity. So increasing temperature causes greater electron scattering due to increased thermal vibration of atoms. Hence the resistivity of metals increases or conductivity decreases linearly with temperature. The total resistivity of a metal is the sum of the contribution from thermal vibrations, impurities and plastic deformation. So scattering mechanisms act independently on one another. Insulators, they have wide band gap. Very few electrons are excited across band gap. Semiconductors, they have narrow band gap, less than 2 electron volt, and more electrons are excited across band gap. Next is magnetic properties. The magnetic field is a force which is generated due to energy change in a volume of space. A magnetic field is produced by an electric charge in motion, for example a current flowing in a conductor, orbital movement and spin of electrons. Orbit of magnetic moment, so orbit motion around the nucleus. Electron considered to be a small current loop generating a very small magnetic field having a magnetic moment along its axis of rotation. Spin of electrons, the spin of electrons also produces a magnetic moment along the spin axis. Spin magnetic moments may be only parallel or antiparallel. Now these are the types of materials: diamagnetism, paramagnetism, ferromagnetism, antiferromagnetism and ferrimagnetism. Next is temperature influence on magnetic behavior. So the atomic vibration increases with increasing temperature and it leads to the misalignment of magnetic moments as they are free to rotate. Above a certain temperature, all the moments are misaligned and the magnetism is lost. This temperature is known as Curie temperature, Tc. The magnitude of Tc varies for material. For example, for iron it is 768, for cobalt 1120, for nickel 335 and for ferric oxide it is 585. Ferromagnetic materials exhibit small volume region in which magnetic moments are aligned in the same direction. These regions are called domains. Adjacent domains are separated by domain boundaries and the direction of magnetization changes across the boundaries. The magnitude of magnetization in the material is the vector sum of the magnetization of all the domains. So as with temperature increase, you can see saturation magnetization keep on decreasing. Then there is difference in soft and hard magnets. So you can see based on hysteresis loops, these type of loops, this is remanence here, this is coercivity. So based on this product, cross product, you get whether your material is soft magnet or hard magnet. So the narrow loop will be the ones with the soft magnets, the broader loop will be for hard magnets. So broad hysteresis loop and narrow hysteresis loop. And the examples include iron silicon alloys, nickel iron alloy and iron, and for hard magnets it is alnico, ferrites, rare earth cobalt and cobalt platinum, etc. Okay, so that's it from my side.